In this lecture, we will start with the topic determining the circuit model parameter of a three-phase induction motor. From our previous lecture, we know the equivalent circuit of a three-phase induction motor can be drawn as this is R1, the stator resistance JX1. This is R2P, rotor resistance, which is transferred to the primary side, JX1, and this resistance is R2P dependent, and this variable resistance depends on the speed of the motor. This is RC, this is JXM. Here the current will be I1, this is the current I2, this is the terminal voltage, the current that is passing through this is IC, and this is IXM. This should be X2 as this is in the rotor side. Now for any real three-phase induction motor, the value of R1 X1, R2P X2, RC and XM are needed to be determined. For determining those values, we need to undergo some tests. These tests are exclusively shown in the labs. However, I am going to describe the methods step by step for determining these unknown values for every motor. So the values that are to be determined are R1, X1, R2P, X2, RC, and XM. In order to figure out these values, we need to go for three different tests. Number one, the DC resistance test. Number two, blocked rotor test. This test is equivalent to our transformer short circuit test. We are coming to that point later on. And finally, number three, no load test. No load test. Let us start discussion on the DC resistance test first. Number one, the DC resistance test. The DC test is done to find the stator resistance R1, this R1 value. Now, if we recall the construction of a three-phase induction motor, suppose this is the stator of a three-phase induction motor, and inside this hollow part we have the rotor. This is the rotor part. This stator is supplied from a three-phase source, and the internal circuit of this stator part can be drawn as like this. We have R1 here, this is JX1. For example, this is the terminal 1 or phase 1, which is similar to this one, and phase B also is having R1 and JX1 as they are having the balance load, and the phase C, it will also have R1 and JX1. So this is phase C, this phase C, phase B, and phase A, phase A. Now, how to measure this stator resistance value R1? In order to measure that value, we need to apply a DC source to any two terminals of the induction motor. So any of the two terminals, this A or B or B or C. For example, this is A, B, C. This is A, B, C. And we are connecting a DC supply to any two terminals, we are choosing A and B. This supply is given through an ammeter so that we can measure this current, that is IDC, and this is VDC, and we can measure this voltage at this terminal using a voltmeter, from which we can get the value of VDC. Now when we'll apply some voltage here, as we are applying DC voltage, so this inductance will have no effect. And this R1 and R1, they are connected in series, so we'll get twice of R1 equal to VDC over IDC. Now this VDC can be measured from this voltmeter, and this IDC can be measured using this ammeter. Once we get these two values, we can get the value of twice R1. So the value of R1 can be written as VDC divided by twice IDC. So once we perform this DC resistance test, we can figure out the value of R1, which is equal to this one. In practical case, we generally apply a small scale DC voltage, as the resistance in the stator side is very low. So to limit the value of DC current, we will apply a very small scale DC supply. Now remember, this motor is run by an AC supply. So when we apply AC supply, the DC resistance and the AC resistance, they will be having different values due to skin effect. So once we calculate the DC resistance, in order to get the AC resistance, the DC resistance must be multiplied with 1.25 to get more accurate AC resistance. So AC resistance R1 can be found out by multiplying 1.25 with R1, which is the DC resistance. So we can say this is R1 DC. This will be the more accurate AC resistance. So the value of R1 is determined by the DC resistance test. Next we will go for blocked rotor test. So second test is the blocked rotor test. In this test, the rotor of a three-phase induction motor is kept blocked so that the rotor cannot move. Remember, when the rotor is blocked and rotor is not allowed to move, and if you give supply, what will happen? The rotating magnetic field will start cutting the rotor windings with the highest value. So what will happen? A huge current will continuously flow in the rotor side as well as in the stator side. So precautions must be taken in this regard. What are the precautions? We are going to describe it later on. First, we need to understand the theory. When the rotor is blocked, the value of slip will be equal to 1. When the rotor is blocked, NR, that means rotor speed, is equal to 0. So S equal to NS minus 0 divided by NS, that will give us the slip value equal to 1. When the value of slip is equal to 1, so what will happen to this variable resistance part? If we put slip equal to 1, so 1 minus 1 will give us 0. This resistance will become 0. So the equivalent circuit can be redrawn as, if I draw it here, we'll have same stator side and the rotor side, and this resistance is 0. So 0 resistance means short circuited, and as this secondary side is short circuited, we can say almost all the current will go through this terminal, because under blocked rotor condition the resistive element is short circuited. That is why this test resembles the transformer short circuit test, as you learned the transformer in your previous semester. Here under blocked rotor condition, we ignored this RC and XM because R2P and X2 are very small with respect to RC and XM. That is why almost all the input current will flow through this R2P and X2. Now let me write R1 here, JX1 here, R2P, JX2. Now till now we have found out the value of R1, still we need to find the value of X1, R2P and X2. Now as we are getting the short circuit condition in the secondary side, then the resulting Thevenin's impedance under block rotor would be much smaller than the rated Thevenin's impedance, which means if we apply rated voltage as the secondary side is shorted, huge current will be flowing through this terminal. That is called short circuit current. From our theory, we know that when the motor is blocked and the rotating magnetic field is rotating, then the relative speed between the rotating magnetic field and the rotor will be the highest, and the highest current will be flowing, and that is the blocked rotor current. That current may cause the damage of the motor. That is why we cannot apply the rated voltage. So in the terminal side, a test voltage must be applied, which should be much smaller than the rated voltage of the motor. Now, in this case, you need to take precautions while applying this voltage. The test voltage should start from 0 and should be increased gradually, and the increment of the test voltage must be stopped when the rated current start flowing through this stator side. So when the rated current will be flowing, suppose this I1 is the rated current, for that whatever the value we get terminal voltage, that will be kept fixed in order to reduce the risk of damaging this motor. So with the test applied voltage for which the rated current flows, the input power can be expressed as, we can write under blocked rotor condition, the input power P in under blocked rotor condition BL can be written as the terminal voltage for which the rated current flows. So we can name it VT BL into the current that is flowing through this terminal, that is the I1. This current can be measured using an ammeter here, and this voltage can be measured using a voltmeter here. So these two parameters are obtainable from our experimental case. So I1 BL into cos theta, that is the power factor. Now here the input power can be measured by connecting a wattmeter at the terminal side. So if we know input power, terminal voltage using the voltmeter and the current using the ammeter, so cos theta can be found out from this equation, P in BL VT BL, that means under blocked rotor condition, I1 under blocked rotor condition, here I1 is the rated current. So from this equation we can find the value of power factor. Now if we consider the total magnitude of the impedance under blocked rotor condition is ZBL, the magnitude of the total impedance under blocked rotor condition can be obtained as ZBL. We are considering the magnitude only, so we can take V terminal BL that was obtained from here, and I1 BL, that is the rated current that we applied here. So once we get the magnitude, we know the ZBL can be written as RBL, that means total resistance under blocked rotor condition plus total reactance under blocked rotor condition. So this can be written in this form. If we know the magnitude of ZBL, so we can write ZBL cos theta plus J ZBL sin theta. Here the total resistance under blocked rotor condition, we can write RBL equal to, what is RBL? The total resistance R1 plus R2P. So we can write R1 plus R2P. Now we can write this real part is equal to RBL. So ZBL cos theta equal to R1 plus R2P, and R2P can be written as R2P equal to ZBL cos theta minus R1. Here we need to take the amplitude. Now we know the magnitude of ZBL from this equation, and we know the value of cos theta from here. Eventually we can figure out the value of theta as well, so we can find the value of sine theta as well. So we know these values, and also from previous DC test we know the value of R1. So once we know all these values, we can figure out the value of R2P. So by employing these equations under block rotor test, we can get the value of R2P. Still we need to find the values of other parameters. Let us continue. From this equation we can say total XBL, that means total reactance under block rotor condition, can be written as equal to ZBL sine theta, which is equal to x1 plus x2. As total reactance is x1 and x2, they are connected in series, so we can write ZBL sine theta equal to x1 plus x2. Now in general, x1 and x2 proportions with respect to xBL, and that is given from the manufacturers. Hence we can separate the value of x1 and x2 from the given ratio. For example, if x1 is given as 0.5 of xBL, and we know the value of xBL as a whole from here, and x2 is given as 0.5 of xBL, then whatever value we'll get, if we divide it by 2, we'll get the value of x1 and x2 separately. For another example, if x1 is given as 0.6 xBL, that means x2 will be definitely equal to 0.4 xBL. So in this way, the ratios are given from the manufacturers. From there we can find the separate value of x1 x2 using this ratio from here. So we can figure out the value of x1 and x2. Still we need to know what are the values of RC and XM. In order to get those values, we need to go for another test, that is no load test. So we'll start the no load test for the 3-phase induction motor. Now under no load condition, the rotor of a 3-phase induction motor is allowed to rotate freely without any load. So the value of slip becomes very low. As the slip is very low, the value of R2 into 1 minus S divided by S goes to really high value. We know if the value of S equal to 0, then it will go to infinite value. But for our case, this S value will be very low when the rotor is running freely. Why? Because rotor is running freely means the difference between NS and NR will be very low. That's why the value of S will be very low. So once the term in the denominator side is very low, then the complete resistance value will go to really very high value. This means we can consider the open circuiting condition for this resistive element under no load condition. Thus, this test resembles the transformer open circuit test. So, under open circuit condition, this portion will be opened. Very insignificant current will be flowing. So, we can consider this portion as open circuit. So, the equivalent circuit can be redrawn here. If we redraw here, so we have similar stator part. This is RC, JXM, R1, JX1, and that's all. we are ignoring this part because this side is open, so no need to draw the remaining part. Now under no load condition, as this portion has very high resistance, so what will happen? A very small amount of current will be flowing in the rotor side. So even though we apply the rated voltage, the current will be very low. So this current I1 under open circuit test, so we can say, or no load test, we can name it NL. So the voltage that will be applied, that is VNL, and that voltage will be the rated voltage of the motor. Now if we consider the total impedance under no load condition, looking from this side is ZNL, we can write the magnitude of ZNL under no load condition equal to V no load, that is the rated voltage, divided by I1 current that is flowing through the circuit, which can be measured using an ammeter, and this V no load can be measured using the voltmeter connected with this motor terminals. So ZNL will be equal to VNL over INL. Oh, I need to write 1 here, I1 NL. Now let us consider the input power under no load condition is P1 NL, and the power at this terminal, power consumed at this terminal, is P1. So we can write P1 under no load condition equal to V terminal under no load condition into I1 under no load condition. Here terminal voltage is the rated voltage multiplied with cos theta, that is power factor. So the no load power factor angle theta can be found out using this formula, P1 NL divided by B terminal, which is rated voltage, multiplied with I1 under no load condition. Again, the voltage across this terminal, suppose this terminal voltage is considered as E1, so E1 can be written as E1 equal to V terminal under no load condition angle 0 degree minus, that means this voltage minus this voltage drop will give us this E1 value. So I can write that voltage drop in this format, I1 under no load condition, angle will be minus theta, as this is the power factor angle, and definitely it will be lagging as we have inductive load here, multiplied with this impedance, so R1 plus JX1. Now let us consider the current through RC is IRC and the current through XM is IXM. So we can write the magnitude of IRC is equal to P1 divided by magnitude of E1. How can we get the value of P1, which is the power consumed at this terminal? This can be found out by using this equation, P1 equal to P1 under no load condition, that is the terminal power, P1 under no load condition, minus the power consumed at this terminal, that is I1 under no load condition square multiplied with R1. So if we can get the value of P1, it's easy to get the value of IRC, that means current through this resistance. Once we get the value of IRC, we can get the value of RC, which is equal to E1 divided by magnitude of IRC. Here we know the value of E1 from this equation, and we know the value of IRC from this equation. So RC is found out. So we can write this RC is found out. Now we are left with XM. The current through this XM, which is IXM, can be found using this formula. IXM equal to I1 under no load condition minus IRC. We can take the magnitude of all parameters. Finally, XM can be found out from this equation. We know the value of E1 and we know the value of IXM. So this voltage divided by this current will give us the value of XM. So XM is figured out. Hence, by applying 3 different tests, we can get the value of R1, X1, R2P, X2, RC, and XM. This is how we can determine the circuit model parameters of a 3-phase induction motor. Based on this theory, you'll have to perform a lab when the lab session will be opened. We'll continue in the next class. Thank you.